There are two traditional approaches to measuring trigonometric function angle rotations. It can either be measured using the degrees or the radian, which we're going to talk about in this video. And we talked about why do we generally use the radians or in degrees in the previous video about the introduction to radian part 1. And we generally prefer to use the radian trigonometric function because degrees with units makes calculation in calculus more complicated. So we're going to review what we did in a previous video briefly and derive the formula about the relationship between the degrees and the radians to convert them easily, basically for graphing the trigonometric function. So firstly, we define the radian in a sector as a measurement of the angle. So for the radian, it is defined as the measurement of the angle along with the degrees that express the ratios. And the radian is basically expressing the ratios or the proportions between two things. The radius, which is half of the diameter, and the arc length, which is part of the circumference of the circle inside the sector. So we basically define the radian in terms of the measurement of angle as a ratios inside the sector. And to review what we did briefly, let's think about one circle with the radius, which is half of the diameter, as 1. So this is the circle with the radius, which is half of the diameter, as 1. And there is a reason why we always assume the radius of our circle as 1 in our trigonometric function. And we will know why as we get to the next video about the unit circle, which is a circle with the half of the diameter as 1. So this is a circle. And the reason why we draw a circle instead of sector is because the circle is a collection of a small or a big sectors. So let's start. So here's a radius of 1. And let's say we draw another radius as 1. So another curved line here will also going to be the radius as 1 because this is the length from the center of the circle, and circumference of the circle will always be the radius. But we won't know today, so radius will just notate that those lengths are exactly same. And this is the definition for a radian. So we can see the arc length between these 2 points or the vertex. We define it as the arc length. And again, the arc length is a curved line that is formed as one of the part of the circumference of our circle. And the definition of the radian is when the arc length and the radius are both equal to 1, which means the radius of our circle, sector, and the arc lengths of the sector are exactly equivalent together. Again, when the arc length, which is part of the circumference of our sector, is 1, also the radius of our sector is also 1, and again this radius and this radius are same radius, then the angle that is formed between 2 radius of our sector and the arc lengths, if we define it as a theta, and again in our sector or a trigonometric function, the theta is a basic notation for the radian measure, then we define it as the value 1. So again, if the arc length is 1 and the radius of our sector is 1, then we define the radian, which is an angle measure that is formed between 2 radius and the 1 arc length inside a sector, as 1. So using this properties, we define the radian as a ratios or proportions between our radius of our sector and the arc length of our sector. And that's why the radian is a ratios. So let's do one more example. But in this case, the arc lengths and the ratios were exactly equivalent. And the next example is what if the arc length increases, because this is a ratio, so the arc length doesn't always have to be equal to 1. So if arc length increases 2 times bigger, with the same radius as 1, then it will look like this. So again, the radius of our sector is exactly equivalent together, but only thing that is different is the arc length. The arc length of this sector, where this arc length is 2, from all the way to here, will be 2. So let's say the arc length is equal to 2 all the way here. And if the arc length of our sector is equal to 2 and the radius of our sector is equal to 1, so again, when the arc length is equal to 2, when the radius is still equal to 1, then we define the data that is between the two radius and the sector arc length. So if we notate in terms of data, which is a radian, we express it as 2. And again, if the radius is exactly equivalent as 1 and the arc length is equal to 2, then we define the ratios between the arc length and the radian as 2. And this is the main subject that we did in our previous videos. But what we're trying to do in this video is trying to derive the formulas that is a relationship between the degrees and the radians. So this was the 2 times bigger, and let's say that what if it goes 3 times bigger? But again, before we do this, we derive the formula between the lengths of the arc and the radians. So we defined if the arc length the length of the arc, if we set it as the L, and if we set the radius of our sector as the variable R, and again, if we set the data, which is an angle in terms of radian, that is formed between the arc lengths and the radius as the data. So again, we already derived formula in the previous videos, where if the arc length, if we notate it as the variable L, and the radius, which is half of the diameter of the sector, as R, and the data in terms of the radian, which is an angle rotations between the arc lengths and the radius, as theta, then we define the ratios or proportions equations or identity in this way. The L, which is the arc length, is equal to the radius of our sector times the theta, which is an angle measurement. So using these expressions, we define the L, which is the arc length of our sector, is same thing with the radius of our sector times the angle measurement in terms of radian. And this was the formula or identity that we proved or derived in the previous videos. And we're just reviewing what we have done. So before we did the third one, we again reviewed what we did here. And again, in this one, we the arc length was multiplied by 2, which means increased. And let's say from the arc length as 1, what if it increased 3 times larger? So again, the radius of our sector will still be equal to 1, but the proportions according to the radius from arc lengths will be 3, like this. So this is a case where the radius of the sector is exactly equivalent with any radius in our sector, but the arc length has been increased by 3 times. So if you say that the arc length, the length of the arc, which is part of the circumference of our sector, has increased as 3 all the way to here. And this is a case where the radius of our sector is 1 and the arc length of our sector is 3. Then we define the angle measurements or the angle rotations between the two radius of our sector and the arc length of 3 in this case, where data is equal to 3. And where the data is equal to 3 means the arc length, which is 3, and the radius of our sector as 1, the proportions between them, which we'll notate in terms of radian data, is 3. And again, we could prove the identity that we used here, that we proved in a previous videos about the ratios between arc lengths and the radius. So this is a case where the arc lengths increased 3 times larger than the original arc length, which was positive 1. And this case, the next case is, what if we increase the arc lengths into the arc lengths as a radius of our circle, the whole circle, but the whole circumference of our semicircle, which is half of our circle. So now we went to the semicircle, which is half of the total circle, and the arc length is from here to the vertex of the end of the circumference and all the way to here, where we can write it as the arc length of this sector. And the arc length of the sector, in this case, the sector turned into a semicircle. But we can realize that the if you want to measure the total arc length from here all the way to here, we could write the arc length as approximately 3.14. And the reason why the arc length is 3.14, and again, the arc length of 3.14 states from the semicircle here and all the way down here. The reason why it is 3.14 is because if it increased to 3 times larger, it is from here all the way down to here, and that is the 3 times of the arc length than the arc length when it was 1 originally. And again, obviously, this arc length, total arc length of the semicircle, is greater than 3 but less than 4, where we can notate it as the 3.14. And the 3.14 is an approximate estimations, where the if it is approximately 3.14, we can write it as the pi. So we can get that the arc length of the semicircle is pi radian in terms of the radian of our sector. But we can actually prove through the formula we already know that the semicircle circumference is pi. So we already know that the circumference of the circle, which is 2 times of the semicircle, is 2 pi r, where it is 2 times the pi, which is approximately 3.14 times the radius of our sector of our circle, and 2 pi r for the circumference of the semicircle. And the semicircle has the half of the circumference of our circle, so it will be 2 pi r, which is the circumference of our sector divided by 2, which is going to be equal to pi r. So the pi r will be the circumference for our sector, but we need to remember that in this case the radius is simplified as 1. So in this case, the circumference for this semicircle will be equal to pi. So that's why we can write the arc length for this semicircle as the pi. So again, with the same radius as the 1, we want to define what is the central angle beside these two radius and the arc lengths. And this is going to be also the central angle for our semicircle. But before we do it, let's review the ratios between the radius and the arc lengths. When the arc length was 1 and the radius of our sector was also 1, then we define the radian between the radius and arc lengths as an angle in terms of radian as 1. And when the radius stays as 1, just like the other radius that we talked about right now, but the arc length, which is a curved line in our sector, increased by 2 times larger, then we define the central angle of data as the positive 2. Thirdly, if the radius is still as 1, but if the arc length increased as 3, Then we notated the main angle as positive 3. So we could realize that the radian was still the ratios between the radius and the arc length. Lastly, if we go approximately 3.1 for larger than the original arc length of 1, where we can notate it as a pi, then what will the main angle will be? Well, we can know that the main central angle, which we'll notate as the theta, will be pi radian, which means the radius, which is 1, times the pi, which is the central angle in terms of the radian, when the arc length is pi, then we could easily solve that the arc length, which is approximately 3.14, was equal to pi radian. And this will happen when the circumference of circle is half as a semicircle. So we can realize in semicircle, and again the definition of the semicircle was the half of our circle, then the central angle, when the L value, which is an arc length, is pi, and the radius, which we'll notate as the r, as 1, then the theta, which I will notate as the theta to show the angle measurements between them, is also going to be equal to pi radian. So again, in the semicircle like we just did here, when the L, the arc length is pi, and the r, which is the radius, is 1, then the ratio between the L and the r in our semicircle, we notate it in terms of the theta, which is a central angle in our semicircle, as pi. But we can think about the pi is in terms of the radian. But now if you think about the central angle in terms of the degrees, we can think about the semicircle's central angles in terms of degrees. We already know that the total circumference of the circle inside the circle's total central angle was 36 degrees, which means from here, if we go 180 degrees even more, then we'll be able to get a total of 360 degrees. But we are thinking about in terms of the semicircle. So what will the semicircle's central angle will become? So the total semicircle central angle will be this big white line. Well, this will be half of the circle, which is 360 degrees, divided by 2, which is 180 degrees. So if it is 180 degrees again, so that means the semicircle's central angle was 360 degrees, which is the main angle of our circle, divided by 2, where we got 180 degrees. That means the total angle rotations for our semicircle, which I will notate it in terms of into the green color. So from this, if you rotate all the way to 180 degrees, which we notate into pi as a radian, then this will be same thing as 180 degrees. And the reason was because we already know that the circle's central angle was 360 degrees. That means the semicircle's central angle will be 360 degrees divided by 2, which was 180 degrees. So we can make a conclusion or the formula where 360 degrees, not 360 degrees, but 180 degrees, which is the central angle for our sector, is pi radians in terms of radian. And this is the standard formula that makes the relationship between the degrees and the radians in our unit circle or trigonometric functions. So 180 degrees is equal to pi radian is the basic formula that makes the difference between the degrees and the radians. Now let's think about the total angle measurements or a central angle of a circle. And we already know that the central angle for a circle is 360 degrees. Where from here, if you rotate 360 degrees for total, we'll get the central angle for our circle. But we don't actually have to calculate it because 180 degrees is pi. So if you multiply 2 to the both side, you will get 360 degrees is 2 pi radian. So 360 degrees is 2 pi radian means the total central angle for our circle is going to be 2 pi radians. So we basically derive the relationship between the degrees and the radian as an expression of the angular rotation, where pi is 180 degrees. And using this proportions or ratios where 180 degrees is equal to pi radians, we could convert it in terms of the data. So we could convert the radians into the degrees or degrees into radians. So let's think about some examples where we need to convert radians to degrees or degrees to radians. So when we're dealing with the radians to degrees or degrees to radians conversion, we always need to remember this fact. So they have the proportions where the theta is an angle measurement in terms of radian over the angle measurements data in terms of degrees always have a proportions of pi over 180 degrees. And if you know what this means, that means in order to convert, let's say there is a special radian or degrees and we want to know it in terms of the other angle measures. So for example, if we know the degree mode, we want to convert in terms of radian modes. Or if you know radian mode, we want to convert into degree mode. And the way to do it is the data, which is an angle measurement in terms of radian, and the data in terms of degree mode has a proportion of pi over 180 degrees. And the reason why we could set it as the equal is because this is a proportion or the ratio. So using these ratios, we could possibly convert radians to degrees or degrees to radians. So we're going to solve it in two different ways, and for understanding the ratios or proportions between radians to degrees, the first one will be we actually prefer to use it, and for the second one, if you want to solve for or convert the radians to degrees or degrees to radians faster, the second one is better. But for the first one, let's say we already know what is pi in terms of degrees. Yeah, pi is 180 degrees. Let's go to the second one, and the second one is we want to know what is 360 degrees in terms of radian. We could double this and get 360 degrees, but we want to use the first one right here, which is the proportions that makes us understand the ratios better. So for thinking about, we already know what degree is, so we want to convert in terms of radians, so we need to use a proportion where pi over 180 degrees is the theta of radian over theta in degrees. So we could write it as, if we don't know what is the radian, so we can set it as the x over the degree, where we already know as 360 degrees. This will have the same proportion as pi over 180 degrees. All you have to do is solve for the x value. So if you rewrite it again, where x over 360 degrees is equal to pi over 180 degrees, to simplify the x value, we need to isolate it by multiplying 180 degrees to the both sides. Or before I do that, let's just multiply 360 degrees to the both sides. And the reason why we're multiplying 360 degrees to both sides is to cancel the 360 and 360 in the denominator to isolate the x term. And we get the x is 180 degrees, and the 360 degrees will cancel out. The degrees will cancel out as 2. So the x value, where we're trying to find the 360 degrees in terms of radian, is equal to 2 times pi, which is 2 pi radian. And this is how we solve the radians to degrees or degrees to radians using these proportions, where pi over 180 degrees is theta radian over theta in terms of degrees. Now let's think about the third one, and we want to solve 90 degrees in terms of radian. And again, we know what the 90 degrees is in terms of degrees. We don't know what is radian. So we can simply write the radian form as x, and we know what is degrees is 90 degrees. It's same thing as pi over 180 degrees. And this is how we solve the proportions between the radians and degrees to solve for it. So let's write this term down again. x over 90 degrees is pi over 180 degrees. To get the x value, which is a 90 degrees in terms of radian, we need to multiply 90 degrees to both sides to isolate it. And if we multiply the 90 degrees and 90 degrees in the denominator, will cancel out, and we will get the x value, which is 90 degrees in terms of radian. 180 degrees, 90 degrees will cancel out as 1 and 2, so we get pi over the 2, where we have 90 degrees in terms of radian is pi over 2 radian. And this is the way where we try to solve the conversion in terms of the proportions. So let's go to the second way. So this is the first one using the second expression, and this is basically using the brain calculation. So let's say we want to solve what is 6 degrees. So using our brains, 6 degrees is same thing with 180 degrees over 3. But we already know what the 180 degrees is. 180 degrees is 2 pi radians. And we have over 3. Oh, it's not 2 pi, it's pi. So we get the 6 degrees is pi over 3 radians. Now let's think about the second one using our brain calculations. Let's say we want to solve what is 45 degrees. We already know that 45 degrees is 180 degrees divided by 4, but we already know what 180 degrees is. 180 degrees is pi radian, but if we divide it by 4, we will get pi over 4 radian, where pi over 4 radian is 45 degrees in terms of radian. Now let's think about the third one, where we want to solve what is 30 degrees. For 30 degrees, we can solve it in terms of 2 ways. We can think about 30 degrees in terms of division from 180 degrees, where we have to divide by 6 to get 30 degrees. Or we can think about as the 6 degrees dividing by 2. But both of them will give us the exactly same answer because they will give us the 30 degrees. So we already know what 180 degrees is. 180 degrees is pi radian, and we need to divide it by 6. So pi over 6 is our answer. Is our answer of 30 degrees in terms of radian. Now let's think about 120 degrees. For 120 degrees, we can think about it into 2 ways also, as 30 degrees times 4, or it's the same thing as 6 degrees times 2, but either way will give us the same answer. So we already know what is 120 degrees. So 30 degrees times 4, where 30 degrees is given as pi over 6. 30 degrees is pi over 6, so this is the same thing with saying pi over 6 times 4. So it is going to be 4 pi over 6. But for 4 pi over 6, they have the common number as 2. So 4 will cancel out as 2, and 6 will cancel out as 3. So 120 degrees is eventually going to be 2 pi over 3 radians. Now let's think about what is the last one, which is going to be 150 degrees. And for 150 degrees, it is same thing with 30 degrees times 5, where 30 degrees is pi over 6 times 5, and that is going to be 5 pi over 6, and we cannot cancel out more. So these were the things that we did for the conversion between the radians to degrees or degrees to radians. So this was the basic introduction for the radian. So we first reviewed what was the radian with some examples where when radian is 1 and the radius is 1 and the arc length is 1, we defined the radian as 1. So using this information, we could derive the formula between degrees and radians, where 180 degrees is equal to pi radian, and we can naturally realize that 360 degrees, which is the central angle for our circle, was 2 pi radian. And also, we could derive the formula and solve radians to degrees in this case. And there are 2 ways to do it. The first way to do it is to use our proportions, where pi over 180 degrees is theta, in terms of radian over theta in terms of degrees. And so the first one, we solved it using this proportion. In the second way, we used our brain calculation to solve all of these questions. And the first one was good for understanding the proportions between the radian and degrees, and the second one was good for solving or converting them faster. But in the next video, where we're going to talk about the new type of approaching the trigonometric function, which is the unit circle. And the unit circle like this has the radius of 1. And so the unit circle, which is the circle with the radius, which is half of the diameter of 1, the thing that we talked about today will be used usefully. So the conversion between the radians and degrees will be used usefully in the next video.